Dzień dobry Państwu. Now, the first question that comes to mind when you see this topic is, what is a knot, scientifically speaking? It is a curve in three-dimensional space which is closed and non-self-intersecting. What does that mean? So let's take this simple piece of string, this shoelace. We can tie it up in any number of ways, and then we can join the ends together. For those of you who remember that Phineas and Ferb episode, these are called the aglets. If you join the aglets, you have a knot. Once you have a knot, you can twist it, turn it, stretch it, squeeze it. As long as you don't cut it open, it remains the same knot. So now that we know what a knot is, let's look at some applications. For that, we need to go on a trip to the mountains. Now, on this mountain, there is a technical section. And to climb this section, we need to rope up. To do this, we tie a simple but effective figure-8 follow-through knot. What is the purpose of this knot? To attach yourself to the rope so that you don't fall off the cliff. That's great. We have done this and we have successfully climbed this slope. And we go a little bit further and we come across a rocky notch. To climb this bit, we need a fixed hand line, which is something that requires a long piece of rope. Unfortunately, we only have 2 short pieces. The solution? A double fisherman's knot, which can be used to join 2 shorter pieces of rope into one longer one, and a secure one. And therefore, we can pass this bit as well. What did we learn on this journey? We learned that the same piece of rope can be tied up in different ways to have different properties. So it's the same piece of rope, but the shape of the knot that you tie with it that determines those properties. 2 knots might look the same to the untrained eye, but they might have completely different uses. So the natural question is, how do we tell 2 knots apart? Mathematicians have a trick. They take these knots and they draw diagrams on 2D surfaces, which for them is a blackboard or a piece of paper. And just like these knots, well, they have different personalities, we can draw an analogy with people. So let's look at a person. He's trying to sign his name. He can sign his name in any number of languages. It could be in Bangla, in English, in Hindi, or in Polski. So too can a knot sign its own name in different ways. But these different ways take the form of algebraic expressions called polynomial invariants. And these polynomial invariants are named after the people who discovered them. One of these polynomial invariants, in particular the Homfly-PT polynomial, which is very powerful and is a generalization of both the Jones and Alexander polynomials, has a connection to the University of Warsaw, because the PT stands for Josef Chitysky and Paweł Tracek, who were formerly or currently associated with this university. So this is all very abstract mathematics, but it turns out that these polynomial invariants also turn up in theoretical physics, which is my field. And we'll get there, but to get there, we need to go on another trip, this time to the beach. So imagine we're walking down this wide open sandy beach, and we come across 3 Bollywood dancers. And these Bollywood dancers, as they're moving around each other in looping circular motions, their footprints trace out paths on the sand. Of course, these paths are plotted on a 2-dimensional surface, which is this beach. But you can take this 2-dimensional surface and add a dimension of time. Once you do that, you have these pictures which look a little bit like these strings that are braiding around each other. These are called world lines, because they tell us not only where the person was at a particular point in space, but also in a particular point in time. Why this is interesting? Well, replace these dancers with special quasi-particles called anyons, which can live effectively on 2-dimensional surfaces. Now, these anyons, as they move and go around each other, they also trace out certain world lines. The order in which these braidings happen, essentially as these world lines twist and turn around each other, the order and direction of these twists and turns, these braidings, are important. A different choice of braiding would lead to different physical properties. In the analogy with the dancers, a different choice of braiding would have led to a completely different choreography, which would have been a completely different dance sequence. This is the idea that underlies topological quantum computing. Now, quantum computing, this phrase, we see that a lot in the news recently. In fact, as recently as yesterday, Google came up with this article that they published in Nature, where they have made some claims about a breakthrough, specifically in verifiable quantum advantage. But the problem with quantum computers as it stands today is that they're highly prone to noise and errors. That is where this picture might come in. Topological quantum computers exploit these topological properties of braiding and aim to store and process information in ways which are naturally protected from many kinds of errors. This is a very promising area of research that several big tech companies like even Microsoft are pursuing. Although a large-scale practical computer is yet to be built, but there has been significant progress in recent times on quantum chips. Now, my own research is a very close cousin of this picture. In particular, if you take the ends of these strings, those metaphorical aglets, and you join them together, then you get again these familiar loops, knots and links. And in a particular closed setting, in a particular framework of theoretical physics that I study, these closed loops can have calculated invariants which reproduce those polynomial invariants that we had previously discussed. My area of research is in trying to study, quantify, and classify the quantum entanglement properties of these knotted quantum states. Now, today's topic is naughty science, and this is all very abstract, and science goes beyond the abstract. So let's conclude with one final example, closer to home, in biology, in fact, within our own bodies. In our bodies, in our cells, we have proteins, and a lot of them. Proteins are these long chains of particular molecules, a set of molecules, which twist and fold in complex ways. But what do you have when you have something that is a long chain, which looks like a string? They get knotted up. So these proteins also get knotted up, at least a small fraction of them. And the shape of the knot that they take determines or influences the stability and the folding pathways. In fact, the knotted structure could also control which area of the protein is most exposed, and therefore this has implications in how molecules, potentially medicine, can act and bind on them through these active sites. This again is something that there are groups at the University of Warsaw who are researching into this field. So that's more or less what I wanted to say about this naughty business in scientific research. I think we can conclude with one final trip, this time into the future. A future where, for certain problems, your local computer, your local device, can execute quantum processes in minutes, what would take a regular computer millions, possibly billions of years. A future where we can read and steer the topology of life itself, designing therapies that might latch on to the correct shape at the right moment, or perhaps even guiding enzymes that manage the DNA topology for treating diseases. So if knots can connect and bind mountaineers to mountains and equations to meaning, perhaps they can bind today's questions to tomorrow's answers. So the next time you're going out and you're tying your shoelaces, remember that the humble knot that keeps the shoe from falling off your feet quietly connects mathematics, matter, and life itself. With that, I would conclude, I suppose, with this one thing that I always wanted to say. Thank you for coming to my TED Talk.